Welcome to another podcast. In this episode, we're going to be taking a look at how to use the Laplace transform to find solutions of ODEs. And in this first example, I want to spend the majority of my time talking about the sort of a general overview of the method, give you a description of what's going to be happening, and some of the terminology associated with the algebraic equations that are generated from doing this. So we're going to start by looking at a very sort of simple differential equation with constant coefficients. As we progress through this chapter, we're going to get increasingly more difficult functions that force the problem. But for now, we're going to stay with something pretty simple. So let's look at ay double prime plus by prime plus cy equals f of t for some forcing function f of t. And I want to solve this because, as we saw in the previous video, if I have any hopes of doing this, I have to supply information about the function for both its for its initial condition as well as its derivative. Otherwise, I can't find the Laplace transform of the derivatives y prime and y double prime. I also want to use the convention that when I try to take the Laplace transform of y, then that gives me capital Y of S. And when I try to take the Laplace transform of f, I get capital F of S. Alright, so let's just sort of blindly apply the Laplace transform to both sides of this equation and look at sort of what falls out. We'll kind of sense our way or feel our way forward on this. If I take the Laplace transform of the left-hand side, that would be the Laplace transform, and I'll just kind of take it step by step here. So this is equal to the Laplace transform of this side. And the linearity of the Laplace transform says that I can pull out any scalars. And then the definition of the Laplace transform for derivatives that we came up with last time says that this will be a times s squared y of s minus s y at 0 minus y prime at 0 plus b, and then here we have the first derivative formula, which is s y at s minus y at 0 plus c times the Laplace transform of y is y of s, and that should be equal to the Laplace transform of f, which is f of s. Now, what I want you to notice is that each and every term on the left-hand side includes a y of s, except for the terms that involve the initial conditions. And so let me go ahead and simplify what we're seeing on the left-hand side. If you look at the parts that are times the y of s, you get as squared plus bs plus c times y of s. And then if you look at the parts that are left over, what you end up having is minus, here we get a y at 0, which we're calling y naught. So a y naught as plus b. So you can see that here. We get a minus as y naught from here and a minus b y naught from there. So remember, y of 0 is equal to y naught. So I'm just taking this piece and putting it here. And then if you look at the derivative, we get a minus a times y prime at 0, but y prime at 0 is my y1, so I'm going to call this y1. And that equals f of s. So the goal of this process is to solve for y of s. So I'm going to isolate y of s on one side by adding over these two initial conditions. I got to remember to call it y naught instead of y at 0 plus a y at 1. And then finally, when I go to solve for y of s, that's equal to, I'm going to break it up into two pieces. First, I'm going to take the f of s and divide by as squared plus bs plus c, plus, and then the second term that we have here, I'm going to divide it also by as squared plus bs plus c. So there's two parts that end up here. There's this part, and there is this part. Now I want to look at what each of those parts satisfies, but before I do that, I want to make a comment. If you look here in the denominator, as squared plus bs plus c, this is the characteristic polynomial. So if I look at the polynomial of this equation, evaluated at s, that is as squared plus bs plus c. So it's interesting to me that we're dividing by the characteristic polynomial to find both of these pieces. Okay, let's start with what I have in red here. So if we're looking at this this first piece here in red, this first piece in red is called the state-free solution. And then the other one is called the input-free solution. So this is the state-free solution, and this one is the input-free solution. Now you should be sort of looking at these saying, well, this looks an awful lot like transient and steady state, and you would be correct. Once we take the inverse transforms of each of these, the inverse transform of the state-free solution becomes the steady-state solution. The inverse of the input-free solution, the Laplace inverse of this, becomes the transient solutions. So these are just the names that are given to them in their algebraic form. This is an algebraic equation. There's no derivatives here. But when we take the inverse transform of both sides, the inverse transform of the left side would be y of t. So this is the goal for this process here. Let me kind of start back up here. If I take the inverse transform of both sides, then the inverse transform of y of s goes back to y of t. The inverse transform of the state-free solution will go back to the particular solution, which we have denoted as being the steady state. And the inverse transform of the input-free solution will go back to being the homogeneous equation solution, y of h. Now, I need to say a little bit more about that. In particular, what is each of these satisfying? The text uses y of s for the steady state and y sub I for the transient because it's mimicking the state free for the s and the input free for the I. But really what's going on here is when I take the inverse transforms of each of these pieces, then I'm solving two different problems. This problem solves y of s, so a y of s double prime plus b y of s prime plus c y of s equals the forcing function f of t with 0 initial conditions. So it's basically looking at what is the response to the force and not the initial conditions itself. The y sub I, on the other hand, it looks at the same equation set equal to 0, so the homogeneous equation, but instead it solves the equation equal to the initial conditions, y at 0 and y1. And so together these two things form a solution to the differential equation, because if you add y of 0 to 0 here, you get y of 0, and y of 1 to 0 here, you get 0. And then if you take the solution to this and add the solution to this, then that makes it equal to the right-hand side as well. And so that's really what's going on here when we're going to take the inverse transform, is we're going to recover one solution to this equation, which is the state-free equation. And we're going to recover a second solution to this equation, which is the input-free equation. And together, both of those are going to be the solution to the differential equation. So really this comes down to, at this point for us in this course, once we've done this process of taking the Laplace transform, are we going to recognize the inverse transforms of the state-free algebraic equation and the input-free algebraic equation? So you're going to see me showcase that in the next video. We're going to look at an example with some numbers here. But I wanted you to understand some of the terminology that goes into this when we're looking at these algebraic equations and then trying to take the inverse transform, turning them back into sort of the same format that we've been familiar here, this sort of steady state part that involves the forcing term and the transient part that involves the initial conditions. All right, thank you for watching.